one of the downsides of k-nearest neighbors is that it is very slow at testing time. The complexity comes from having to compare the testing point to every training point. And we briefly mentioned why that's the case, right? So if you have a little data set, let's say in 2 dimensions, and you want to quickly find all the nearest neighbors for this red point, to you as a human, it's obvious because you look at it and you immediately see the nearest neighbors. Right? It's a little different for the algorithm because the algorithm doesn't see this picture, the algorithm sees that picture. It sees a list of instances and attribute values for all of those instances. So really the only way to figure out what the nearest neighbors are is to take the testing instance and to compare it individually to every single one of the training instances. And that is slow. That involves n times d comparisons, where n is the number of training instances and d is the dimensionality you're working on. So the way you deal with it is you either try to reduce d by doing similar technique like feature selection, or you try to reduce n. And the way this works is you try to quickly and roughly guess a number of potential nearest neighbors, m. So you hope m is bigger than k, but it should be a lot smaller than n. So you do a rough first pass at getting the potential nearest neighbors, and then you just compare the testing point to those m potential nearest neighbors. And the question is really, how do you find those potential nearest neighbors? So we'll briefly talk about three different ways of doing that. KD trees is appropriate. It allows you to find m potential nearest neighbors if you're working in a low-dimensional and continuous space. So if your instances have relatively small attributes, and relatively small, think, a couple dozen, so 10, 20, 30. And they're all real valued, so the data is not sparse, it's dense and it's low dimensional. KD trees are a good technique for that. You get a substantial reduction in the cost of finding nearest neighbors, but it comes with a price. The algorithm can miss nearest neighbors. If you have the opposite of this case, if your data is high dimensional and sparse, you can borrow a page from search engines and use something called inverted lists, and I'll mention what those are. They give you an attractive complexity, and one nice thing about inverted lists is you don't miss nearest neighbors, so it's an exact technique. If your data is high dimensional and it's not sparse, you cannot use inverted lists, but you can use something called locality-sensitive hashing. It's a technique that in some ways reminiscent of KD trees, and we'll talk about the similarities and differences. It has attractive time complexity, but again, just like KD trees, it can miss the nearest neighbors that you have.